Hey everyone, welcome back. So, does it ever feel like your friends just have more friends than you do? I'm here to tell you that that's not just a feeling, but it's a mathematical fact. Today we'll be talking about a very interesting problem called the friendship paradox. The reason I love this problem is because it brings together a lot of different areas of mathematics, namely statistics and also graph theory. And you'll see that we'll start with a toy example here for why this might be true and why it seems less like a paradox after we go through this example. But then we'll go to the mathematical proof, which I have to say is one of the most interesting mathematical proofs I've worked through. Not because it's complicated. In fact, it's not too complicated. But again, because it blends together really interestingly these areas of statistics and also graph theory together. So we're going to start here with this toy example, this toy network of 5 ghost people. And each of them is connected to some other ghost people via these edges, which represent friendship. So for example, A is friends with B and C is friends with everyone, D is friends with E and C, and so on and so on. Now let me throw out a little bit of graph terminology so that when we get to the proof, it's a little bit easier. These ghost people, in the context of graph theory, are the nodes of the graph. So this graph has 5 nodes. These connections or friendships between ghost people are called edges in the graph. So all you really need to know are their nodes, 5 nodes, and there's 6 total edges in the graph, which represent these friendships. Now, let's start filling out this data table and calculate those 2 numbers we care about. The first is, on average, how many friends do you have? And the other one, of course, the other part of the friendship paradox is, on average, how many friends do your friends have? So the rows of this table represent each ghost person, A, B, C, D, and E, and I've kept the colors consistent, hopefully, throughout so you can keep track of who is who. This next column here is the number of friends that each person has. So if you're A, you have 2 friends, B and C. If you're B, you also have 2 friends, A and C. If you're C, you have 4 friends, everyone else in the network, A, B, D, and D and E also have 2 friends each. So we can actually calculate the first part of the friendship paradox already. We can say, on average, how many friends do you have? And to do that, pretty straightforward. We know the total number of friends everyone has. We just add all those numbers up, divide by 5, and we get that on average, you have 2.4 friends. So that's the first number we filled out here. Now things get more interesting. Now we want to know the second part of the friendship paradox, which is, on average, how many friends do your friends have? And so the first step there will be to enumerate who is each person's friends, which we've done here. So A is friends with B and C, B is friends with A and C is friends with A, B, D, E, and so on and so on. Now the next thing is, for each of these friends lists, how many friends do they have? So it's getting a little bit meta, but hopefully we can follow along here. Let's look at a concrete example A. A is friends with B and C. We say for B, how many friends does B have? B has 2 friends. How many friends does C have? C has 4 friends. And we fill out everyone else in the table just like that. Now, in order to compute, on average, how many friends do your friends have, we're going to be adding up all the numbers in this friends of friends table. So how many numbers are there total? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers. And we're going to divide the sum of those 12 numbers by 12, because that's the total number of entries in this friends of friends column. When we do that, we get 2.67, so we can fill out the other blank here, which says, on average, you have 2.4 friends, we already know, and your friends have, on average, 2.67 friends. And so at least for this small example here, your friends, on average, do have more friends than you, because 2.67 is bigger than 2.4. Now, let's break this example down a little bit before we go to the proof, because the more we break down this small example, the easier the proof is going to go and the more interesting the proof is going to be for us. Now, the first caveat I'll say is that this entire friendship paradox is talking about on average. What the friendship paradox is not saying is that no matter who you are in this social network or in the world, no matter who you are, your friends have more friends than you. That, of course, would be impossible because there is some person out there in the world with the maximum number of friends, and by definition, none of their friends can have more friends than them. For example, C has 4 friends, and so because they have the most friends in the network, there's no one out there with more. It's just a statement about the averages. If you're the average person, then your friends have more friends than you. Now, the other thing I want to do here, because we have a nice simple visual to look at here, is start looking at why certain things are true. So for example, you notice that when I counted these, there was 12 total entries in this friends of friends column. Now, how many edges are there in the graph? There's 6 edges, 1, 2, 3, 4, 5, 6 edges. It's not a coincidence that 12 is 2 times 6. And that's going to be one of the really important findings that we're going to carry over when we look at the proof of this friendship paradox. Why would the number of entries in this friends of friends column be double the number of friendships in the graph? Well, let's think about the number of times each edge gets counted. And let's do it again by considering ourselves as A. So if I'm A, then when I go construct this friends of friends lists, the first time my connection to C, for example, gets counted is when I consider, well, I'm A, one of my friends is C, and that's the first time this edge between A and C gets counted. So this edge between A and C is so far counted one time when we're considering A as our current person. Now, when is the other time that this edge between A and C gets counted? Well, it's when we consider C as our current person. Putting ourselves in the shoes of C now, we're asking, who are your friends? Well, A, B, D, and E. And therefore, that's the second time the edge between A and C gets counted. And thinking about it, this edge between A and C will not be counted in any other case because it's only relevant to these two people, A and C, by definition. Therefore, each edge in this network gets counted exactly twice when we're constructing these arrays of friends, which proves that the number of entries in these friends of friends list is exactly always going to be double the number of friendships or edges in the graph. That's going to be a very important result which we'll carry forward. And the other result that we'll carry forward right before we go to the proof here is looking at what makes up the sum of these 12 numbers. And this color coding really does help here because we can look at the number of times each number occurs in this sum. So let's just start calling out some observations. For example, this blue 2, which corresponds to the number of friends that B has, how many times do you see a blue 2 in this array here? You see it once here and you see it once here. So this blue 2 shows up twice. Now, how about this purple 2? This purple 2 also shows up twice. Now, what about this green 4, which represents the number of friends that C has? This green 4 shows up 1, 2, 3, 4 times. So this is a small example, but it sure does seem like the number of times that a particular number shows up is the value of that number itself. This 2 shows up 2 times. This 4 shows up 4 times. Now the real question is that just a coincidence or is it a fact? And let's show here that that is actually a fact because that will be the other very important trick we'll need for the proof next. And let's do that by considering this 4. This 4 again is the number of connections that C has. Why would this 4 need to show up 4 times, contribute 4 times to this overall sum that we're computing here? Well, think about the number of times that we consider C's friends. It's going to be exactly the number of connections that C has. Because, again, putting ourselves in the shoes of each ghost, if we consider A, then we have to consider the number of friends that C has, which is 4. If we consider B, we have to consider the number of friends that C has, which is again 4. Consider D, you have to consider the number of friends that C has, which is 4. And again, considering E, you have to consider the number of friends that C has, who's a friend, which is 4. And so this 4 is guaranteed to show up 4 times. In other words, 4 times 4, or 4 squared, is the total contribution coming from C's friends. And you can make the same exact argument for anyone else in this diagram. For example, looking at D, this orange 2, which corresponds to the number of friends that D has, shows up twice because that 2 is considered when you're putting yourselves in the shoes of C or putting yourselves in the shoes of E. So this orange 2 shows up twice, in other words, 2 times 2 or 2 squared. So the total sum that we're considering here, the numerator of our fraction used to compute this 2.67, is going to be the square of the number of connections coming out of each of our ghosts. And the number of connections coming out of each node has a much simpler name in graph theory. It's simply called the degree of that node, and you'll often see that as degree, and then you'll put the node index down here. So the degree of C is 4, the degree of D is 2, and the degree of everyone else here is also 2, because that's the number of connections coming out of that node. So the numerator is the sum of the square degrees. So if we sum up the square degrees of all the nodes, that is the numerator of our fraction. And the denominator of our fraction is twice the number of edges. So if you haven't seen these, looks like absolute value bars, but in the context of graph theory, that is the size of the edge set, or the number of edges in the graph. And for completeness, the size of the vertices set is going to be the number of vertices in the graph, which is 5. Believe it or not, through this simple toy example, we have just made our lives infinitely easier, and we're going to breeze through this proof of the friendship paradox now. So let's get into the proof, the fun part. So here's the proof. The first thing we're going to do, the first part of the friendship paradox, as we said, is what is the average number of friends that someone in our social network, or now let's just open it up to the world. What's the average number of friends that someone in the world has? We're going to call that mu. So mu is going to be the average number of friends someone in the world has. And that's pretty straightforward to compute. You simply add up from I equals 1 to the magnitude of the vertices sets, the number of people in the world, the degree of each vertex. In other words, you go visit every person on Earth and you ask them, how many friends do you have? And then you divide that total by the number of people in the world. That's pretty much how you take an average. No surprises there. And now what happens if you add up the degree of every single vertex in the world? Well, if you add up the degree for A, then you're counting each of A's edges once. If you add up the degrees for B, you're counting each of B's edges once. And you can see again, using the same logic we're using before, that if you add up the vertices for every single person in the world, you're going to count each edge twice, once from the point of view of A, for example, and once from the point of view of the other person, the person on the other end of that connection, which is B. And therefore, the sum of the degrees of all the vertices of the people in the world is twice the number of edges in your graph. So the average number of friends that someone has is 2 times the number of edges in your graph divided by the number of people in the world, or number of vertices in your graph. So let's keep that result here. Now, an intermediate result that's going to be extremely helpful to compute for us is the standard deviation of the number of friends that someone has. So here we found the average is 2 times edges over vertices. Now let's figure out the standard deviation, a little bit more involved, just a little bit of algebra to be honest. So we're going to call that sigma squared. So actually in this case it would be the variance. So let me be more proper here and just call this not standard deviation, but variance. So the variance of the number of friends that someone has, sigma squared. Let's appeal to the definition of the variance. So the variance of anything is the sum of the squared deviations divided by the total number of things you care about. So now we just expand the inside and you get 1 over the number of people in the world. I just took this 1 over v on the outside. di squared minus 2 mu di plus mu squared. That's just expanding the square here. Now, let's push this sum through each of these 3 terms here and see all the simplification magic that starts happening. The first part is pretty straightforward, sum of di squared, nothing magical going on there. Then, this 2 mu we can actually pull out of the sum because it's a constant, and that leaves a sum over all of the degrees in the graph, and as we already know, that's going to be 2 times the number of edges, which means that this next term simplifies quite nicely to minus 4 mu number of edges in the graph. And finally, this mu squared also has nothing to do with the sum. We can pull it out. And when you sum over, well, a bunch of 1s, it's just the number of items in the sum, which is again, the size of the vertices set or the number of people in the world. So it's not extremely trivial to get from this line to this line, but if you go ahead and do it for yourself or you pause or rewind, confident you can get there. Now we have this 1 over v hanging out here, so let's push that through each of these terms we have. The first term doesn't really look much different. It's the sum of the di squared, all divided by v. Then we do minus 2 mu, so I'm kind of breaking this up a little bit because I want to recognize a term we already know about. So 2 mu, which leaves a 2 times edges divided by the vertices, which comes here. And we get a very nice cancellation for the last term where we get a vertices size in the denominator and a vertices size in the numerator, which just means we have a mu squared here. Simplifying one more time here, this part is unchanged. What is 2 times the number of edges divided by the number of vertices? Well, boom, we know that is exactly the definition of mu. So we get minus 2 mu squared plus mu squared here. And so bringing to our last page of the proof here, let me just put this above for a second so we can make sure everything lines up. That means that the average number of friends that someone has is 2 times the number of edges over the number of vertices. And the standard deviation, variance of the number of friends that someone has is going to be sum of the squared degrees divided by the number of people in the world minus mu squared. I got this minus mu squared by doing one last simplification up here because minus 2 mu squared plus mu squared is just a minus mu squared. Okay, now, why did we go through all the trouble of calculating the variance? Because it's going to help us calculate the other quantity we actually care about in this proof, which is, again, the average number of friends that your friends have. So if we want to know the average number of friends that your friends have, what's the procedure there? The procedure, let me bring this back here, would be to visit each person one by one. So visit A and say, yo, who are your friends? B and C, B and C. And then count up how many friends each of those people have, and do that for everyone in the graph. And so this sum, this double sum, while it might look a little bit scary, is basically just doing that procedure in mathematical form. So on the outside, I'm going from each person in the world from the 1 to the size of the number of people in the world, so it's going to be visiting each person in the world. And the inner sum is saying for each person in the world, visit from j equals 1. This is not a delta, this is an fi, which is the set of friends that you have. So for each person in the world, I'm visiting all of that person's friends, and I'm counting the degree of that friend, which is the number of friends that that friend has. I've definitely said friend way too many times. And so that's what that sum is doing. And this is an average, so we need to divide by something. And what is the denominator? What should the denominator be here? That's where our observation that the denominator should be 2 times the number of edges in the graph comes in super handy. So I can just put here 2 times the number of edges in the graph. And this inner part here also becomes super easy because as we said, as we showed before, that's actually just the sum of the squared degrees of everybody in the graph. So we didn't even need to really do this double sum. I just thought it would help to start from first principles and then simplify that using a observation that we saw in this toy example here. So this is actually, as we said, the sum of the square degree of everybody in the graph. And this denominator here, again, carrying over is 2 times the size of the edges, or 2 times the total number of friendships in the graph. Now, believe it or not, we're basically done with the proof. We have all the results we need. We just need to sequence them in the proper order. The first thing I'll do here is take this formula for the variance that we've proven and rearrange it just a little bit. So I'm going to add mu squared to both sides. So you get sigma squared plus mu squared here. And then I'm going to multiply the size of the number of vertices, or the number of people in the world, on both sides. And you get the result that the sum of the squared degrees of everybody in the graph is equal to this number of people in the graph times sigma squared plus mu squared. And the reason, now you see why it was important to calculate the standard deviation, because now we have a formula for the sum of the squared degrees of everyone in the graph in terms of just sigma and mu and the number of people in the graph. So that means that if I were to take this quantity, the sum of the squared degrees, and I divide that by 2 times the number of edges, then that's going to be the same as dividing this right-hand side by 2 times the number of edges. And now we make one last observation. What is v divided by 2e? Well, if you flip that, you see that that's exactly mu. And so that means we can put mu in the denominator here. And so all of this simplifies to sigma squared plus mu squared divided by mu, which again, you can just break up the top part and put the denominator on both of these terms. And you get this is equal to mu plus sigma squared divided by mu. Whew, let's take a deep breath there. I know that wasn't a trivial amount of math, but let's calmly walk through what we have shown here. The average number of friends that your friends have, we said, was the sum of the square degrees of everyone in the graph divided by 2 times the number of edges in the graph, which is exactly what's written right here. We showed that that is equal to mu plus sigma squared divided by mu. And this thing, here's the last thing we need to say. This thing, which is the average number of friends that your friends have, is greater than mu. Why is this greater than mu? Because it's mu plus, well, something positive. The variance has to be a positive number, and mu has to be a positive number because it represents the average number of friends in this case, which can't be negative. Therefore, we have shown here that the average number of friends that your friends have, this quantity here, is bigger than the average number of friends that you have. And that is the end of the proof. We can draw our little QED box to make ourselves feel happy, and we have shown this result. The only caveat I would say, you might be wondering, why is there not a greater than or equal to here? Technically, I should put a greater than or equal to here, but that only holds, that equality would only hold if sigma was equal to 0, which means the standard deviation of the number of friends in the world for each person is 0, but that would mean that everyone has the same exact number of friends, which is simply not true. So hopefully you found this proof kind of interesting. I've recently rekindled my love of going through proofs. It's just been really fun, and I've been away from it for a long time since I was a student, but it's always fun going through a cool proof that is based on intuition that you have built up. And of course, this video is not meant to be depressing in any way. This friendship paradox is only a statement about the number of friends that your friends have being bigger than the number of friends that you have, again on average. There is no mathematical proof that the quality of friendships that you have is less than the quality of friendships that your friends have. And as we know, friendships are more about the quality of friendships than the quantity. So think of this more as just a fun little problem than any statement about your life. So hopefully you guys enjoyed this video. If you did, please leave a like and subscribe, and comments below are welcome. Thank you so much for watching, and I'll see you next time.